All right, this starts Physics 2. And Physics 2 begins with Chapter 13, where we start to build the concepts behind electromagnetism, which forms the core basis of what we cover in Physics 2. All right, so looking at 13.1, I need to introduce a couple of new concepts that are going to be the basis of this whole unit of physics. And these are electric fields and magnetic fields. Now, you've already had some familiarity with both of these, so we know the Earth has a magnetic field. If you've ever done any experiments in elementary school with static electricity, you've seen the impacts of electric fields. Well, now we're going to learn the equations behind these observations that you've already had. And as you've probably already noticed, these are more abstract concepts than what we talked about in Physics 1. So it'll be a little bit different of a visualization process in mastering the types of equations that we do in this semester. All right, so moving on. So this is physics. Physics is all about forces. So now we need to start relating electric charges and force. So we're going to start with electric charges, and we're going to see that this is going to crescendo into something beautiful by the end of this class. So if you recall from Physics 1, the concept of a point particle. So essentially, this is a particle where we took all the mass of a system and concentrated it into a single point. And this allowed us to simplify several calculations. Now, sometimes this was acceptable and sometimes we needed to do an extended system. But remember, point systems are always easier to calculate. So all mass at a point. But I need to introduce something called a point charge. So this is similar to a point particle, but now you have, instead of all mass, you would have all charge at point. Now for some things like electrons and protons, the point charge is basically the system. So and for some macroscopic objects, it is sometimes acceptable to use the point charge approximation. But we're going to develop when and how over the next couple of chapters. And you'll see the games that we play. All right, so this is, of course, the study of forces. So let's look at the Coulomb force law for point particles. So we know that E and M is one of the four fundamental forces. And Coulomb's law describes the electric force. So the magnitude of the electric force, so please note that I am writing F without a vector since this is a scalar, and in this case it's the scalar magnitude. So this is equal to 1 over 4 pi epsilon naught Q1 Q2 over R squared. So for this equation, Q1 and Q2 are the magnitude of electric charge. So in this case, the sign is not included. And this is for point particles. R is the distance, which is always a scalar quantity. And the electric force acts along the line between the two charges. just like gravity. So gravity would act on that line between the star and the planet, for example. Now, with charges, so gravity is simply an attractive force, whereas electromagnetic force is attractive and repulsive. Only attractive. And E&M is attractive and repulsive.
Unknown caller.
So like repels, unlike attracts. And two charged objects will interact even if they're not touching. All right, so let's look at the units and constants of Coulomb's law. All right, so the SI unit of charge is the Coulomb. And the charge of one proton is E is equal to 1.6 times 10 to the minus 19 coulombs. Electrons have a charge of minus E, sometimes written E to the minus. So please note that the value E within electromagnetism is just going to stand for the standard unit of 1.6 times 10 to the minus 19 coulombs, which is the charge of, or the absolute value of the charge of electrons and protons. So if you're looking for the electron, look for the minus associated with the E instead. Okay, so the constant 1 over 4 pi epsilon naught is equal to 9 times 10 to the 9 Newton meters squared over Coulomb squared. Now in this class we shall always be writing out this full value because this is actually the true constant. The constant is actually epsilon naught. So in some books you'll see this written as a K. We do not write it as a K because that's not the constant. The constant is epsilon naught, which equals 8.85 times 10 to the minus 12. And we're going to see something really cool late into the semester from preserving this constant in its pure form. All right, so there's a couple commonly charged particles, or common charged particles that we're going to see quite a bit. And I'm just going to go ahead and list them. So we have the electron, which has a mass of 9 times 10 to the minus 31 kilograms, charge of minus E, we have the positron, which is the electron's antiparticle, same mass, 9 times 10 to the minus 31 kilograms, charge positive E, same size. Proton has a mass, it's much larger, 1.7 times 10 to the minus 27 kilograms, charge positive E, radius of about 1 times 10 to the minus 15 meters. Antiproton, same mass, 1.7 times 10 to the minus 27 kilograms, opposite charge minus E, same size. And then you might occasionally encounter something with a muon or something like a pion. So we have muons. They have a mass of 1.88 times 10 to the minus 28 kilograms. And they can have charge positive E if you have a mu plus, or negative E if you have a mu minus. And then you have pions. Mass of 2.48 times 10 to the minus 28 kilograms. Mass of plus E if you have a pi plus particle, or minus E if you have a pi minus. All right, so the last thing I want to say on this section of chapter 13, so we're going to start thinking about matter in terms of its charges. So if you recall atomic structure, you have a very tiny, dense nucleus with protons, which are positive, and neutrons, which are neutral. And then around that, you've got the electron cloud of negatively charged electrons. And atoms, in their natural state, are neutral in their charge. So there's enough electrons for every proton. And we're going to see what the consequences of this are as we progress through the study of Physics 2.